Hello, everybody. So today we're going to take a look at using some balancing equations and some stoichiometry and trying to figure out how to get going with all of that information. So we're going to take a look at a couple of different things. Specifically today, we're going to be looking at stoichiometry as a way of addressing what's going on in a chemical equation. So there's going to be kind of a series of these. You may need to watch all or none of them, just depending on what your comfort level is. So feel free to fast forward past the boring parts. That's not everything, but feel free to pass forward past those. So the first concept, just in general, what is stoichiometry? It's kind of a weird looking word, right? Stoichiometry. And it's really a fancy way of saying that we're going to use balanced chemical equations as a recipe, as a way for us to be able to interpret what's happening in a chemical equation or chemical reaction. So I'm going to start with a real recipe. This is grandma's pound cake, right? So if we're dealing with actual recipes, right, there it is on the screen. If I gave you a recipe like that just said eggs, butter, flour, sugar, go, and said, okay, make it. The family's coming for Thanksgiving or coming for Christmas dinner. We want to have this famous pound cake dessert here for dinner. There's more information than you need than that, right? All we've got on here is a series of ingredients, right? Our reactants. And the picture kind of shows us what the product should be, right? Magic. And somehow these happen. But we're definitely missing some important pieces when you think about what's required for a recipe to be useful. A recipe is not the same as a shopping list. And a lot of times when students start doing chemistry, they kind of forget that there's another component to those recipes, and that's the quantity side of it, right? It's not just a qualitative piece, but quantitative. We need to know what ingredients are going in, but we also need to know how much of each ingredient is going in. By the way, I don't know if you know this is why it's called pound cake, because that's literally how you make it. There's 4 ingredients. You use a pound of each. Frightening, actually, how much butter that is. But that's basically what pound cake is. So when you've got a recipe like this, not only do you have that list of ingredients, but then you also have some things like directions, like combine. Is it just mix in a bowl? Do you need to use a blender? What do you need? And then you need some sort of like energy piece to it. Bake it for how long, etc. These are all the pieces that we have in a typical chemical reaction. And with this recipe, one of the things that I want to point out that is obvious, but we forget when we start talking about chemistry, is that recipes are scalable. In other words, I can make as many multiples of that recipe as I want to. Or if I want to say be good to my waistline, maybe I only want to make a half of a recipe. I can scale it up or I can scale it down. And if you think about it, the scaling process is actually pretty straightforward if the ratios are easy. So if you need to make 6 pound cakes for the bake sale, you know that all you have to do is multiply everything by 6, right? Pretty straightforward. How about if you only have a quarter pound of butter? Well, if you've got a quarter pound of butter, then you're only going to be able to react it with equal amounts, right? A quarter pound of eggs, a quarter pound, what's a quarter pound of eggs? A quarter pound of flour, a quarter pound of sugar, etc. And you can scale it down. The problem is, of course, in chemistry, a lot of times our recipes aren't quite this easy. And so the scaling process is a little bit more challenging. But the idea is still exactly the same. So when we're talking about this in chemistry, what's the similars, what's the differences to this one? So number one, when you have a recipe, you've got these important ingredients. You have your list of ingredients. These are called reactants, right? You have your expected products, right? It should be a pound cake or whatever, a dozen cookies or whatever it is. There's usually some sort of an energy requirement. A lot of times early in chemistry, we don't worry too much about the energy side of it, but is it energy in, energy out, and how long? And then you also have the key part at the bottom there, the 2 things, the expected quantity of products, right? If you didn't know like how many cookies is it going to make or how many pound cakes, is that 1 or is that 5? How many is it? The other part is that you have now a ratio. And that's the key part, that you have a way in that recipe to be able to scale the number of reactants that you have to the amount of products that you desire. That scaling process is really the thing that we're looking at. And that's what actually stoichiometry is. It's using balanced chemical equation. So here's our multimole example, taking this from the science side to the chemistry side. So we're going to use a real simple here equation, which is the equation for the synthesis of water from hydrogen and oxygen gas, which is actually pretty exothermic, believe it or not. It gives off a lot of heat. So we have our recipe, right? Our 2 ingredients are hydrogen gas and oxygen gas. And we have 1 product, and that product is liquid water. We also have in here an implied ratio. So if we take a look up at the top, right? Hold on, I need to get my pen out of the way, sorry. There it is, there's my pen. Give me my pen, there it is. If we take a look up at the top, right? We've got a ratio. We've got 2 of these is going to react with 1 of those and make 2 of those. So that really means that we have 2 parts hydrogen to 1 part oxygen. In our pound cake, I know it was 1 to 1 to 1, so it was a little bit easier. But this is 2 parts of hydrogen to 1 part oxygen, kind of like an Oreo, right? 2 parts cookie, 1 part filling makes a cookie. Actually, this would make 2 cookies, I know. But when we're dealing with this ratio now, it's our balanced equation. There's our recipe. There's our list of ingredients here on the left. Here's our list of products here on the right. In this case, there's only 1 product. Not always 1, but in this case, there's 1 product. And we have our set of ratios to this. So let's think about scaling our recipe. If we've got 2 moles of hydrogen and 1 mole of oxygen, I can make 2 moles of water. Perfect. What if I have 4 moles of hydrogen? Well, I'm scaling my recipe, right? My recipe starts with 2 moles of hydrogen. If I've got 4, I'm basically doing this, right? I'm scaling it up. So how much oxygen do I need? Well, I need that 1 oxygen times 2, right? I'm doing the scale process. If you get to funkier numbers, though, it can be a little bit more awkward, right? I still maybe don't know exactly how much I'm going to get for product, but if I have 6.7 moles of hydrogen with excess oxygen, excess here means I simply have more than enough. I'm not going to run out of oxygen. How much water can I produce? So this is a little bit harder to see, right? Because I don't know if I'm going to 2 to 6.7. That's some kind of weird random amount. But I can look at my equation and look at my ratio. Look, I've got 2 moles of water go in. Well, that also means I have 2 moles of water that go out. So if I have 6.7 moles of hydrogen that go in, I could get 6.7 moles of hydrogen out. I can use my ratio. Now, we can do this with dimensional analysis. And this is the key part, that if we start to have odd numbers, this is how it actually looks. So again, if it's numbers in your head, sometimes it's easier. But if I'm trying to go from 6.7 moles of hydrogen to random moles of oxygen, well, I kind of know it's like half, right? Half of the hydrogen becomes oxygen. It's a 2 to 1 ratio. So I could go, well, half of 6.7, what's half of that? I can kind of figure that out. Well, let's make the math a little bit easier. We're going to use dimensional analysis. It's a Wunderfraction, yeah. So we're going to start with what we are given, 6.7 moles of H2. And now here's the trick. Our chemical equation up above gives us the ratio that we need. If I'm just going to go to water, I know that 2 moles of hydrogen in is going to make 2 moles of hydrogen out. I can use this like a conversion factor. 2 moles of hydrogen is going to make 2 moles of H2O. And so I know my 2's are going to cancel out, right? Divided by 2, I'm going to get 6.7 moles of H2O. And that other problem, I talked about the oxygen, and I just talked about this verbally, 6.7 moles of H2. But now I want to go to oxygen. Now, do I multiply by 2? Do I divide by 2? And again, you may have an instinctive knowledge, but let's let the equation guide us. In our equation, 2 moles of hydrogen will react with 1 mole of oxygen. So I can set up my equation, moles of hydrogen on the bottom, and then moles of oxygen on the top, O2. And it's 2 moles of H2 makes 1 mole of O2. And it makes it really clear exactly what the math is that we need to do. I do 6.7 divided by 2 and get whatever that value is. I don't really care what the answer is, but you would literally do 6.7 divided by 2. And it makes the math much more easy. So our balanced equation, the coefficients can be used like conversion factors. And that's kind of a handy thing for us. So here's a little bit of a scarier looking one, right? I'm kind of building it up. So again, here's our balanced equation up at the top. 1 mole of Fe2O3, which is iron 3 oxide, will react with 3 moles of sulfur trioxide to produce 1 mole of Fe2SO43. That's iron 3 sulfate. So there's our balanced chemical equation. So if I want to use up 1.83 moles of sulfur trioxide, okay, 1.83 moles. I'm demonstrating a technique if you're not great with the math part of this. See, I'm labeling my equation. It helps me know where the numbers go. What's related to what. And I want to know how many moles of iron 3 sulfate will be produced. So I want to know this one. iron 3 sulfate. So I can set it up. Start with what you're given, 1.83 moles of SO3. Again, now notice I did not put that coefficient in there yet because I just know that I have 1.83 moles of iron 3. What am I doing? Sulfur trioxide. Nice. Very good. Very good. So now when I do my conversion, I know it's 3 moles of SO3 will produce 1 mole of Fe2SO43. It's a crazy thing to say, right? So follow your units. Let the reaction, let the equation, the recipe be your guide. Moles of SO3 go on the bottom. Okay, why? Again, we always cross our units down. And we want to we're going to convert to moles of Fe2SO4 3. So that's what we're trying to do. Those are our two things, the in and the output. And then I just use my recipe. Well, 3 moles of sulfur trioxide will make 1 mole of Fe2SO43. And sometimes students ask, well, what about the other material? Well, I guess we're kind of assuming that we have enough of that to go around, assuming that that's not the thing that we're going to run out of, so we don't have to worry about it. It's still there, but it just means that we don't have to care about it mathematically speaking right now. So this tells us what our math is. How much can we do? Well, 1.83 divided by 3 will give us our total number of moles. And my handy dandy calculator, 1.83 divided by 3 is 0.61. 0.61, and that's a 0 at the end for 3 sig figs, moles of Fe2SO43 could be expected here. So last one right here, what mass of product will be created? What mass? Wait, I haven't talked about mass yet. Okay, so think about the pound cake. Notice how when we did the pound cake, it was 1 pound of eggs, 1 pound of butter, 1 pound of sugar, 1 pound of whatever. And you made 1 pound cake. But I promise you that 1 pound cake does not weigh 1 pound at the end. Law of conservation of mass says it doesn't weigh 1 pound. So there's something different here that's going on. When we are using our ratios here are always in moles. Moles, right? How would we figure out the mass of product that came out of this? Well, we're trying to figure out mass. That's grams. And if we know what product it is, it's this Fe2SO43. It's actually a pretty straightforward conversion. We know we've got this. Can you convert from moles to grams? Of course you can. It's called molar mass, right? 0.610 moles of Fe2SO43. We're trying to figure out mass. We're going to do moles of this stuff, Fe2 ... to grams of Fe2 ... Well, this is a molar mass step. So how do we get molar mass of Fe2SO43? Man, that's a lot. So Fe2, I got to find iron. Iron is, it is not 4. Nice. I believe it's 54. No, it's not. It's 55 point. Epic fail on my little thing there. I'm going to have to fix that. 55.84. 55.84 times 2 plus, we've got 3 sulfurs. Now I'm curious now. Yeah, 32.06 is right. Plus 32.06 times 3 plus all of my oxygens. And my oxygens are 16 times 12. Yikes. That's a big, heavy thing. 399.86. So again, with this times 0.610 to give us our final answer, we get a value of this, 243,914, something other like that. So with our 3 sig figs that we've got going on, it'd be 244 grams of product would be made. So again, once you're in moles, our ratio is always done in moles to moles. That's what our recipe units are always, moles to moles. And then if you want to do converting to grams or finding something out about mass, you just do a molar mass conversion. Pretty straightforward. So there you go. I hope that helped kind of get you started on the idea of using chemical equations as a type of recipe, right? Reactants in, products out, and the ratio. So you can start to predict your amounts of products or your amounts of reactants that you need. So there you go. Hope you have a good day.